Number 24. A 0.05 kilogram ice cube at negative 30 degrees Celsius is placed in a 0.4 kilogram of 35 degrees Celsius water in a very well insulated container. What is the final temperature? All right. Tough question. Okay, so just be prepared. It'll probably require a detailed explanation. All right, so we're trying to find the final temperature, right? And we know that the water inside this container is starting at 35 degrees Celsius. The ice cube here is starting at negative 30 degrees Celsius. So when this ice cube is dropped into the water, what do you think is going to happen to the temperature of the ice cube? Should it go up or down? Good, it should go up, right? And then how about the temperature of the water in there? Should it go up or down? It should go down, right? So basically what you just told me is that whatever heat is being lost from the water is being gained by the ice cube, right? The heat, the temperature of this is going up, the temperature of this is going down, and therefore the heat is traveling this way, right? Energy is traveling from the water into the ice cube, okay? Now let's just formalize that in terms of an equation, all right? We can say now that the heat energy lost, so I'm going to put a little negative sign there, okay? The heat energy lost for the water should equal the heat energy gained by the ice. Okay? And these signs are very important for this problem. You have to plug in these signs here. Okay, so hopefully that should make sense. Now this is the big idea of the overall problem. Okay? Now, from here, we have to ask ourselves first, will this ice cube melt? Okay, and the reason why I asked that, why I'm asking that question to you, is because if we think about how to calculate, right, these problems, you know, I suggested you use a continuum. Okay, you separate the solid, liquid, so that's an E, solid, liquid, and gas phase. You plug in then the melting point here and the boiling point here. Okay, so the melting, we're talking of water, right? So it's 0 degrees Celsius is melting or freezing, right? And boiling or the condensing point is going to be 100. So we have two things, right? We have an ice cube that is beginning all the way over here at negative 30 degrees Celsius. That's the ice, okay? And we have now liquid water that is at an initial temperature of about 35 degrees Celsius, right? So the problem here is that you know what's the range, by the way, if I ask you a question, what's the range of the temperature? What range, the final temperature should fall into which range? Well, it should be somewhere greater than this value, right? And somewhere less than this value. So you know it's going to fall somewhere in here, right? The problem is, though, where it falls will be very significant in terms of how you calculate the problem. If the final temperature falls here versus if it falls right at 0 versus if it falls in the liquid stage, right, somewhere between 35 degrees and 0, will change how I calculate the problem. So the first idea is to figure out whether this ice cube will melt, and will it fully melt? Okay, that's really the key question to start. Will this ice cube melt? So how do we figure that out? Well, you can think about it this way, that in order for well, first let's calculate then the energy that's necessary to fully melt the ice cube, okay? To fully melt that ice cube. So in order to do that, there's two steps to the problem, right? If we look at our diagram up here, we have to go from solid ice from negative 30 degrees Celsius to 0. And then we also have to take into account this phase change. So there's two parts to this calculation. So one, we're going to use Q is equal to MC delta T. We're talking about the heat gained, by the ice here will equal the mass of the ice, the specific heat of ice, and the change in temperature of the ice. So the mass of the ice, they told us, was going to be 0.05 kilograms. Specific heat of ice, you just got to look that up, 2090 joules per kilogram Celsius, 2090. And then multiplied by the change in temperature for the ice. Now the ice, again, we're trying to see if it's going to fully melt. Therefore, the change in temperature of just the solid, of just the ice, is from negative 30 to 0. So the final is 0 minus then a negative 30. Okay? And if you notice here, lo and behold, the sign here will be negative, right? Which we should assume, excuse me, the sign will be positive, what am I talking about? Which is correct. All right, because it's gaining heat, right? So 0.05 times 2090 times then basically 30. And here we have now 3,135 joules of energy will be required to get the ice to 0 degrees Celsius. Now, once it gets to 0 degrees Celsius, we then now would like to calculate if now the ice will fully melt. So we have to take into account the heat energy necessary to cause the ice now to turn into liquid. So that's where this formula comes in at the top, right? So Q is equal to now mass M times L. So this is the heat necessary for a phase change will equal then the mass of the object that is changing phase multiplied by the latent heat of fusion or vaporization depending upon what you're doing. Solid to liquid, liquid to solid is fusion, liquid to gas, gas to liquid is vaporization. So here we're talking about basically the heat necessary to melt, so that's heat of fusion basically, right? The heat energy of fusion here is going to be equal to the mass, and again, that's still the same ice, so it's going to be 0.05 multiplied by then this value comes right from the table. Now just be careful because this is in kilojoules. So what I'm going to do here, because I already have a value in joules, I'm just going to convert this to joules right away. So just multiply by 1,000. And now lo and behold, we'll do 334. That looks like a 9, I know, times 0.05, but it is not. So this is 16,700. So this is 16,700 joules. Okay, so we know that in total now, right? We know in total that it's going to take this amount of energy to change the temperature of the ice from 30 to 0, and then it's going to take this amount of energy to cause the phase change to occur. So why don't we add them together to find then that total, okay, to get the ice to change phase. So basically for the ice to fully melt, okay, and just get to 0 degrees Celsius, it would just be the summation of those two. So add then the 3,135 to that 16,700, and now we get 19,835. So this represents the amount of energy that it will take to get from ice at negative 30 degrees Celsius all the way to liquid water at 0 degrees Celsius. Okay? So this value basically represents ice going to liquid. Okay, solid going to liquid. Let's put that on up there. Now, so let me ask you a question as I'm erasing. How do you think now we can figure out whether the ice is going to melt? Well, we have to turn our attention to now this part. Okay, we have to find out how much energy there is, all right, inherent inside of this mass of water, all right? And the energy that's really what I'm saying inherent there is how much energy would be necessary to take out of this mass of water in order to go from 35 degrees Celsius to then 0 degrees Celsius. Okay, how do we find that out? Well, again, it's fairly straightforward. It's just now the same formulas we used before, MC delta T. And we can say now the heat that would be lost, right, by the water would equal the mass of the water multiplied by the specific heat of the water multiplied by the change in temperature of the water. So let's just figure out how much heat we'd have to take out in order to get this water down to 0. All right, so it basically be QW is equal to the mass of the water. They told us it was 4 kilograms. Specific heat of water is 4184 or 4186. Some of the values slightly different because it changes with temperature actually. And then the change in temperature of that water, we're starting at 35. Excuse me, we're ending, it's final minus initial. We're ending at 0 and we're starting at 35. So it's going to be negative, and that should make sense because it's losing heat energy. So 0.4 times 4184 times then 35, negative now, negative 58,576. 576. Okay. Let me just make that a little nearer. 58,576 joules. So now what we just found is the amount of heat energy that it would take that that water would have to lose, in order to get that water down to 0 degrees Celsius. So if you just think about this now, this is the amount of energy it takes, right, to get the ice to fully melt and turn it into liquid water. This amount of energy that's inherent in this 35 degree Celsius water, if we were to lose the energy going to 0 degrees Celsius now, it far exceeds, right? The negative sign just tells you basically inflow or outflow, whether it's losing or gaining heat. Don't look at this as, that this value is less than that. It's not, okay? You cannot have negative energy. It's either zero energy or some energy, right? It's the negative is just losing or gaining. So this magnitude far exceeds this magnitude. And what that basically tells us now is that we know that the final point here, the final temperature will lie, focus on the diagram up here, the final temperature will lie somewhere here. I know the ice is going to fully melt. Okay, now that helps me now with the calculation, okay? Because now basically it becomes fairly straightforward, okay? So here now, let me just bring this on up and put that aside. And now, let's perform the last part of the calculation, okay? So we're going to go now back to this. Now that we know that the ice will melt, now I know how I can think about this problem, okay? So basically, I probably don't even need this value anymore, actually. I'm just going to get rid of it. I don't really need it, okay? And I don't want it to stay up there to distract you. It was just to figure out whether the ice will melt or not. Because like I said, it depends where this final point is. It will depend on how I set this equation up now. So we know the water, when it loses heat, will not change phase. The water, right? It's going to stay a liquid. So I can expand on this now, right? I know I can use this formula. Okay, so let's start plugging in. So it's negative. So it's the mass of the water, right? Because that negative sign gets carried over. It's the mass of the water multiplied by the specific heat of the water multiplied by the change in temperature of the water. Okay? Now that will equal. Now let me set this all up, okay? And then I'm not going to calculate again because we already did. But let me set it all up. So now we know that the heat absorbed by the ice there's going to be 3 phases to it. One phase here in yellow, another phase here in blue, and then the third phase will be somewhere from 0 to that final temperature. Okay? So I basically have 3 parts to this piece here. So we would say now the mass, and this is all positive, so I don't have to put a sign in front, it's just positive. So there's the mass of the ice multiplied by the specific heat of the ice multiplied by the change in temperature of the ice, plus then the phase change, the mass of the ice basically that melted multiplied by the latent heat of fusion, then plus now the mass of the liquid water. Do not confuse it with this. The mass of the liquid now, remember the mass of this liquid came from the mass of the solid ice. So this number here is not 0.4, it is 0.05. You have to be consistent with these units, with these variables, okay? This is all about ice. So the mass of the ice portion is 0.05. If the ice goes from a block of ice to then a liquid portion of, right, the liquid portion, the mass hasn't changed. The volume might have, right, because, ice expands, but the mass is the same. So now, let me just move this over slightly so I have a little more space. So then it's the specific heat of the liquid water multiplied by the change in temperature of that liquid water. Remember, this is coming from the ice block, not from this. Okay, so now we already calculated this. That's just what we did over here. Right? So notice, this now becomes nice and simple. Okay, I'm going to plug in things that I know now. So this is negative. The mass of the water inside of the container was 0.4 kilograms, right? The specific heat of the water is 4184. The change in temperature then, the final, I don't know what it is, so just leave it as a variable, minus the initial for the water was 35 degrees Celsius. Okay, that takes care of that. Now equals this thing we just calculated. So this is 19,835 plus then the mass of the liquid that came from the ice, right? So it's 0.05 multiplied by the specific heat of the liquid, that's 4184, because that's what it is. And then the change in temperature again, and let me just move this piece out of the way one more time, sorry guys, is going to be then the final temperature, I don't know what it is, minus then the initial, okay, which it started at, if you think about this, right, this is the ice cube we're talking about, it started at 0 degrees, and then it went to this final value of something. I don't know what it is. That's what we're finding. But just take a step back. Take a step back and just look at this thing, right? Look at it. We have one unknown. Isn't that the whole goal? To solve for one unknown? Now we can do it, all right? Just consider how this problem might have changed, right? The problem may have changed if the ice cube didn't melt and instead all of the water here froze. Then essentially what I did over here for the ice, I would have had to have done here for the water. I would have had to talk about the latent heat of fusion of this mass of water, etc. Okay, that's why you have to know first if it's going to melt or not. Otherwise, you can't calculate it. All right? So now it's just math. The physics is over. It's just math. So I'm sure I can already hear some of you guys, oh, great, it's just math. Oh, that's a joy, right? That's just a joy. 4184. Okay, so we're just doing the multiplication here. So this is going to be a negative now. I'll just distribute the negative. It's going to be 1673.6 multiplied then by the final temperature minus 35. And that will then equal now this 19,835 plus then 0.05 times 4184. And this is 209.2, 209.2. And multiply TF minus 0 is just TF, right? Okay, so basically this is our new equation. So what I'm going to do, copy this just quickly, 1 second. I think that parenthesis might be coming along for the ride. We'll see. Yes, it did. No problem. All right, so now let's try to finish this up at the top, okay? I'm just going to get rid of this work. Actually, let me just do it this way. It's a little faster. How you guys doing today, huh? Hopefully you're having a good day. I know I am. Any day I do physics is a great day, right? It actually kind of becomes a little interesting, right? Come on, you got to give that to me a little bit. It's a little interesting, right? Especially if you begin to learn how to approach this, right? I always use this analogy. Imagine you don't know how to play the piano, and you sit down at the piano, and you're going to begin to play. Is it going to be any fun? No, it's not going to be any fun. But imagine you start to learn how to play it now. You got to put in the effort to start learning. But then as you start learning a song here and a song here, oh, I want to learn this song or that song, it all of a sudden becomes more fun. And that's the same way with learning anything. It's always difficult in the beginning, but the more time you spend and the more you learn, the more interesting it becomes because you become better at it. It's actually a little more motivating. It's like a positive feedback cycle. So just stay determined. And at least I'm giving this advice to you halfway through the book, right? Maybe I should have said this in the beginning chapters. Anyway, all right, let's, enough of that. So let's distribute this value. So this is going to be negative 1673.6 times TF, plus then, because there are two negatives now, 1673.6 times then the 35, 58,576. So 58,576. Then will equal now 19,835 plus then the 209.2 TF. Okay, combine like terms. So basically, I'm going to bring this guy on over to that side. I'll just, you know what, let's just show it now. Plus 1673.6 TF plus then 1673.6 TF. And then I'm going to then subtract this, right? The 19,835 minus the 19,835. And lo and behold, let's see what we come up with. 58,576 minus 19,835. 38,741. So 38,741 will equal then, let's add those together, 209.2 plus 1673.6. There is always opportunity for error as soon as you start doing all this math all over the place. 1882.8 TF. and I'll just double check at the end, make sure the answer is reasonable. And if it is, we're good to go. 1882.8. All right. Just always calculate it right on your own. Just double check me. Okay. So here we'll get 38,741 divided by then that value. And we're going to answer of about 20.6 or so. Right, 20.6 degrees. So 20.6 degrees Celsius. This is what the final temperature will be. Now this sounds reasonable to me. All right, it doesn't sound too far off. So I think this should be good. I don't think there was any mistakes anywhere. But you know, anytime you do long calculation, there might be. So that should now make sense, right? I mean, we said that the water here should have gone down in temperature. So it started at 35, and now we realize it ended at 20.6 degrees. And then the ice cube began at negative 30, and it now rose to 20.6 degrees Celsius. So should all make sense. Guys, I appreciate you tuning in. All right, I really do hope this video helped. If it did, give us a hand. Hit that subscribe button. Actually, more importantly, if we did help you out at all, some of your classmates or friends might also find these videos helpful. If you wouldn't mind, you know, sending them our way, it'd be so much appreciated. You take care.